Well, may I have your attention, please? Today I wanted to talk about another type of interaction. It is referred to as magnetic interaction. This semester, actually, we spoke only about one interaction. It was an electrostatic interaction. Now, can you remind me what affects electrostatic interaction? Or what determines what is the value of the, let's say, electrostatic force? It's what? Spin doesn't. Charge of the particle. This is the attribute of a particle which affects electrostatic interaction. Correct. What else? And actually, charge of what? Charge of the subject or object of interaction? I mean, subject or the source of interaction? Both, actually. A charge of the object which exerts a force, charge of the particle on which the force is exerted. What else? Relative position, right. Anything else? Nothing. Nothing else. Yeah, so electrostatic interaction depends on charge of the subject of the source, charge of the object on which the force is exerted, and position, relative position of the two objects. Just recall Coulomb's law. In Coulomb's law, we have Coulomb's constant, which is a constant, physical constant, and then attributes of the two particles interacting and the distance between them and unit vector which indicates the direction. All right, magnetic interaction depends on one more thing. Yeah, there is a type of interaction in which actually the force depends on velocity of the particle. So if a particle, we'll see that if a particle doesn't move, the force is zero. If a particle starts to move, the force is not zero. Classical physics actually explained this interaction only in terms of velocity. Modern physics, however, in 20th century, we started to make experiments in which actually we concluded that velocity itself cannot explain interactions. And in 1929, concept of spin was introduced. So now we recognize that magnetic interaction depends additionally on velocity and spin of the particle. It still depends on the charge of the particle and still depends on relative velocity of the particles. Now the reason that it is that electrostatic and magnetic interactions are combined together results from the fact that actually, depending on how we look at the situation, we would recognize that it's different. So let's say that I have this, I will borrow these capsules and pretend that these are particles. And let's say that they both that these are two charged particles, that the caps are two charged particles. And now, when I start to walk with constant velocity in the reference frame of the classroom, well, I can assume that both reference frames, the classroom and my reference frames, are inertial reference frames. A classroom is pretty close to inertial reference frame, and if I walk with constant velocity, then my reference frame is as good as the classroom's reference frame. Now, how I see the particles and how you see the particles. Well, let's start with you. What type of interactions you would, let's start with me. What type of interactions I would identify for those two particles? In my reference frame, how the two particles move? They don't, correct. So how I would interpret their interaction? Electrostatic, correct. Now, how about you? in your reference frame, both particles have velocity. Well, then you would recognize that, that there is magnetic interaction too. There is electrostatic interaction. From your reference frame, you would recognize that it is combination of electrostatic interaction and magnetic interaction. Therefore, we are not able really to separate, because depending on this, how we look at this, we can identify both interactions or only one. All right. Yeah, so let's say that we have a certain particle which travels and enters a region in which magnetic interaction exists. Then this particle will start to move in a circle. It is going, if magnetic field has uniform, in the space has uniform magnetic field, so the properties are of the magnetic field are the same throughout larger space, then the particle is going to move along a circular path with a constant angular velocity. So I mark here angular velocity of the particle, and the particle will move in a circle, which means actually that what is the direction? I'm assuming magnetic interaction is a relatively strong interaction. So, and actually, if the particle moves in a circle, it means that the net force actually results from that magnetic interaction. So, if only magnetic force is exerted on the particle, it is going to move in the circle. So, what is the direction of magnetic force then in this drawing? If this particle moves in the circle, well, which way? Up. Magnetic force is up. Let's figure out why. Why magnetic force is up if the particle turns in a circle? Who believes that it's up? Who believes that it's a different direction? Nobody. Well, those of you who thought that that the force is in the other direction, you were right. Force is obviously not up. Well, because what is the direction of acceleration of the particle? Which way, Owen? Not clockwise. Acceleration is not clockwise. Which way? Not counterclockwise. Toward the center, right? Toward the center. In order for an object to move in a circle, there must be a centripetal force. So the net force has to be toward the center. Yet think about it. How can you make an object to move in a circle? Can you? Yes, Adam. How could you do it? Yeah, put an object on a string and swing it, right? So it is going to move in a circle. Now, why is it going to move in a circle? Where the centripetal force comes from, Adam?
It's coming from the motion.
Not from the motion, from the string. You are pulling it toward the center. You are holding that string, and that string pulls the object toward the center. Well, the same thing happens over here. We need a centripetal force. Well, since this is a case in when the object is only under influence of magnetic interaction, so magnetic force must be in this direction. All right. The region of space in which the magnetic forces are exerted is called a magnetic field. It's the same way as we recognize that the region in which gravitational forces are exerted is called gravitational field. A region in which electrostatic forces are exerted is referred to as electric field. Now, in case of electric field and gravitational field, we have a physical quantity which describes it. And it leads directly to a force. So what was the physical quantity which described electrostatic field, which led directly to the force? If I multiply that quantity by appropriate attribute of a particle, I obtain the electrostatic force. What was that quantity? Charge times what gave me force? Which quantity describing electric field? Electric field vector, correct. Now recognize that book calls it electric field, so there is a confusion. There could be a confusion. With magnetic field we have the same situation. Magnetic field is described, so at each point we have a certain physical quantity. It's a vector quantity which describes the property of the magnetic field at that location, and that quantity, according to the book, is called magnetic field. I want to call it magnetic field vector, at least for a while, until we really become so comfortable that we can skip word vector. But magnetic field vector is a physical quantity which describes properties of the magnetic field, the space. And it is defined in a particular way. Well, it's the simplest, actually, the simplest way to describe magnetic field, although it is not as simple as description of electric field. But it's the nature of nature. Nature gave us magnetic interaction like it is, and we could not describe it in a simpler way than we do it. We have to use a vector product, and the reason for it is that the magnetic force happens to be perpendicular to velocity. So we have to find out such an operation which would result in force to be perpendicular to velocity. Now, whenever we calculate vector product, the result happens to be perpendicular to both factors, which means that it is going to be perpendicular to velocity. It happens to be automatically perpendicular to magnetic field vector, but we didn't have choice. We have to construct it in such a way because we have this product available, and no other product will produce a vector perpendicular to a factor. All right, so let's say that magnetic field vector is straight up. Actually, the same way as we draw magnetic electric field lines, we can draw magnetic field lines. Let me remind you how electric field line is drawn. It is such a line that at each location, electric field vector is tangent to the line. The same thing is for magnetic field lines. Magnetic field line is such a line that at each point, magnetic field vector is tangent to that line. So, but if I consider, for example, this point, I marked here magnetic field lines. So what would be the direction of magnetic field vector at that location, at this location? Straight up, correct, straight up. All right, now let's say that we have a particle in the moving in this magnetic field, and magnetic field vector at the location of the particle is straight up. Let's figure out what is the direction of the magnetic force. Now we will have to refresh our memory about this, how we calculate vector product. Anybody remembers? Christy, do you remember how to calculate vector product? How to determine the direction of the vector product? We have already done it, right? Can we refresh our memory for what quantities we use vector product? When did we introduce vector product for the first time? I mean, no, when we applied vector product for the first time. We applied it actually to describe to describe interaction using a particular quantity, which was very useful for analysis of rotational motion. Torque, correct. When we discussed torque, yes, so torque was a vector product. And Jerry, could you remind us, it was vector product of what and what? Position of a particle and the force exerted on the particle. All right, so this was, for example, an example of vector product. Now, torque describes interaction, and actually what we were doing from the very beginning, from the first class when we met, we were trying to link interaction to predict future, how the objects would rearrange themselves. So we always linked interaction with motion. Torque referred to interaction, which quantity referred to motion, which was linked to torque? A few of them. Angular momentum, right? Rate of change of angular momentum was equal to the torque, right? And how about, I recall we had a formula that torque equals I alpha. What was that? I stands for moment of inertia, and alpha stands for... We cannot forget whatever we discussed half a year ago. We have to remember that. Alpha was, yes, Eric?
Reference angle?
Not reference angle. Angular acceleration, correct, angular acceleration. All right. Anybody remembers how to multiply? We say? Oh yes, we could use determinant, right? So if we wrote vectors, both vectors, in terms of their scalar components, we could use a determinant with the first row of unit vectors I, j, and k. I mean unit vectors of a right-handed Cartesian coordinate system, I, j, and k, to be more specific, and then calculate the determinant and find what? Components of the product. Right. Now, anybody remembers how to use right-hand rule to determine the direction? Yeah, because I mean, indeed, what Jens recalled, it allowed us to accurately find all scalar components, or all components of the product, and indeed for calculations it's the best way. Use the determinant. But just to figure out geometrical relationship, we can use right-hand rule to recall the direction of the product. So let me remind you again how to use it, how to use right-hand rule. And it's up to you actually how to use it. You can develop your own way of remembering it, to remember directional relationship. Right-hand rule is just a trick which we use to relate, to remember how to relate it. And the way I do it, first I align my entire palm with the direction of the first vector. Yes, so consistently with the drawing over here, I will have to align my hand this way. I want all of you to do it. Align first the hand with the first vector. Now you have to rotate your hand until you are able to bend these four fingers in such a way that they are aligned with the second factor. Yes, so magnetic field vector is up, which means that I have to orient my hand like this. Yeah, from this location I cannot bend the fingers in the direction of the second vector. Now the thumb indicates the direction, which direction perpendicular to both vectors, I have to choose. So, consistently with right-hand rule, the magnetic force exerted on this particle is going to be toward us. All right, now let's see. Now let's relate actually the angular velocity of the particle moving in magnetic field to the quantities which describe the situation. In other words, to velocity of a particle and the value of magnetic field in which it is moving. So in other words, magnetic field vector. Yeah, so let's say that I can recognize now that in order to have force toward the center, magnetic field has to be down. Can you see it? Well, let's use the right-hand rule again. Yeah, velocity of the particle is toward us. So first I will align my hand with the direction of velocity. Now, I know actually that the force has to be to the left. Yes, so I start now following the thumb and rotate it until the force agrees. So I see that the magnetic field had to be down, right? Now let's do it the other way, consistently with the formula for the force. So if I recognize that magnetic field is down, I will first align the palm with the velocity. Now I turn my palm until I'm able to bend my fingers consistently with the magnetic field vector. Thumb shows the direction of the force consistently with the drawing. I would like also to remind you something from Physics 1. A certain fact about uniform circular motion, or circular motion actually. In circular motion, centripetal acceleration happens to be equal to the vector product of angular velocity and velocity. If we take a look, for example, at the direction, can you see? Oh, yeah. Let's find out that indeed that this is centripetal acceleration. Why don't we try to multiply angular velocity and velocity? And can somebody help it? To align his or her hand properly. Because, looking at the drawing. So first we have to align the palm with angular velocity, which means that I have to, how do I have to orient my hand? Straight up, correct. Now I have to rotate my palm until I'm able to bend the fingers in the direction of velocity. Well, so it means that I have to do it this way. I recognize that the acceleration is toward the center. It's consistent with the direction of the magnetic force. Can you see it? All right, now let's perform calculations and relate precisely acceleration to velocity and magnetic field and the charge of the particle. This is what magnetic force is going to depend on. Well, in the presence of if the particle is only under influence of magnetic interactions, so then the net force is equal to magnetic force. Well, so I can write down that acceleration of this particle is equal to net force, which happens to be magnetic force, divided by mass of the particle. And magnetic force depends now on this, how the particle moves and what is the magnetic field vector and the charge of the particle. So I wrote now this expression from the previous slide for the magnetic force. It's charge of the particle multiplied by velocity of the particle multiplied using vector product magnetic field vector. On the next, in this step, I just rearrange the factors. Yeah, one thing about vector product is that it is not commutative. So be careful whenever you calculate vector product, that it matters what is the first factor and what is the second factor. However, vector product is anti-commutative. So if you change the order of factors, you will get an opposite result. Therefore, instead of if I change the order of velocity and magnetic field, yes, over here I had velocity multiplied by magnetic field. Here I have magnetic field multiplied by velocity. These two products are opposite to each other, so I had to put minus over here, and I copied Q over M. I copied Q over M. It doesn't matter which factor of the vector product we multiply by a number. I wanted to put it next to B for a particular reason. What's the reason? This. I wanted to write it down that I have velocity multiply by a certain vector. Here is a certain vector. I know that in a uniform circular motion, the first factor is angular velocity. We multiply angular velocity by velocity to get acceleration. Here I have acceleration is equal to certain vector multiplied by velocity. Well, so what is my conclusion? In a uniform circular motion, in a uniform magnetic field, the particle moves with a constant angular velocity, which is aligned with the magnetic field vector. And actually, it is, if a charge of a particle is positive, angular velocity is in opposite direction than magnetic field vector. It's over here. We had magnetic field down, angular velocity is up. If charge were negative, then the particle would move clockwise on this picture. What did I say? No, if a charge, right. So angular velocity would be consistent with the direction of the magnetic field vector. And I have a simulation. So I like to pull it out. In which actually we can now play and see how the particles would move. So this is a charged particle, and here I can change various quantities. I can adjust magnetic field, charge of the particle, and mass of the particle. Well, I had a certain default values. Well, it's not obvious what is the direction, however, of magnetic field. I want you to figure it out. Now I will run the simulation, and the particle starts to move this way. Why don't you have a conversation with each other and figure out what is the direction of magnetic field to obtain, to force a charged particle to move that way. Now, charge of this particle is, oops, what? All right, so charge of a particle is one elementary charge. So we can think about it, and mass is equal to mass of one proton, which means that the particle is what? Charge of a particle is one elementary charge, and mass of this particle is equal to atomic unit. What's the particle? Proton, correct. It's a proton, right. I did not put units for magnetic field, and we will have to have a relatively high magnetic field to make a proton to move in a small circle. So let's run it again. All right, so this is with a, actually with this one we don't see exactly how it moves. How about if I make that field actually weaker? All right. Figure out what is the direction of magnetic field vector. How about approximately? I mean, let's say that it's this way. Am I on the right track? Is it this way? The direction of magnetic field vector. All right, well, you figured out that it has to be perpendicular to the plane of motion. Most of you are showing me that way. Well, some of you are showing it that it's into the whiteboard. Some of you are showing that it's out of the whiteboard. All right, now, so who believes that it is into the whiteboard? I mean, into the screen, actually. Who believes that it's out of the screen? I think more of you believe that it is out of the screen. So can somebody volunteer? I mean, it is out of the screen. Would you be willing to give an explanation?
I don't know if I can give an explanation. I just use the right-hand rule.
Use the right hand, and this is what you were supposed to do. Yeah. So why don't you tell us how you figured out that it is out of the screen?
Well, I just use the right-hand rule for the velocity.
All right, on which side?
The velocity.
Because velocity is changing. Yeah, but so let's stop. Let's stop actually the simulation and let's analyze it at a particular instant. Okay, so wherever it stops. All right, it stopped over here. So now velocity of the particle at that point was downward, right? Okay, I buy that.
Okay. Then the force from this way, the inside towards the center.
Right.
So the thumb points outward.
You misaligned your hand.
Oh, okay.
Yeah, because the fingers, all the fingers. I mean, unless you use it that way. But I prefer actually that you align, yeah, because let's write down the formula again. So let's stick to the way I did, because it's possible that you use the right hand rule differently, and if you are consistent, it would work. However, the way I wanted to use it was first to align the fingers with velocity, the 4 fingers with velocity, which means that consistently over here we will have it down, right? Oh no, you are right. Sorry, you are right. Yeah, so first we align the entire palm with velocity. Now we recognize that the force is to the left, so I have to align the thumb with the force. And I'm able to bend the fingers in this direction. So magnetic field indeed has to be toward us. This is correct answer. Now, does anybody else have another explanation? Not going 2 slides backwards, but just one. Christy, do you have it?
Just that it's going the opposite direction as the last slide.
Right, something is going in the opposite direction. What is going in opposite direction to what? You are right, yeah? Anybody is catching up what she's talking about? Because the charge is positive, so what is opposite to what? Now say it in English. I'll let Christy to say it. B is opposite to omega. Yeah, say it in English now. B was, yeah, this is a new phrase. This is a phrase which we learned today. B stands for
Field vector.
Yeah, magnetic field vector. Yeah, and omega is a quantity which we learned last semester. It is
Velocity. velocity.
Angular velocity of the particle, correct. Now, if the particle moves clockwise, well, angular velocity is in, which means that magnetic field is out. Thank you, Christy. All right, let's now run a simulation, and I'm going now to play with various things. Actually, why don't you tell me what to change? What do you want, Christy, what would you like to change? The charge. All right, let's change the charge. Charge. And how would you like to change the charge? Make it stronger or weak? I mean, big, higher or smaller? Smaller. Well, did you predict that motion this way? Well, if the charge was 0, well, if you look at the expression for magnetic force, it disappeared, right? This is why the particle started to move along straight line. Why did it change now the direction? Because now it rotates counterclockwise. And indeed, this is what would happen. This simulation is accurate. If instead of using protons, we use electrons, it will start to rotate the other way, the opposite way. Well, take a look at the expression for the force. Velocity is not dependent of charge. Correct. The result of this entire product depends on the charge of the particle. If I change q to minus q, the direction is going to change. I will get an opposite vector with the same velocity and the same magnetic field. All right. Now figure out what will happen if I increase magnetic field. Consult with each other. What will happen if magnetic field were stronger? Anybody? Force will have a greater magnitude. Correct. The force will have greater magnitude, which means that how the path is going to be affected. The path will become smaller. Correct. Yeah, because centripetal acceleration will be greater. All right, I'll move it now. All right, how about if I reverse the direction of magnetic field? What will happen then? What will happen? It will spin down. It will spin the other way. Let's see if Oscar predicted it properly. And indeed. Well, how about if I increase mass? It doesn't matter on the path. Who agrees with that? Angular velocity will change. Shall I do it? Well, not only that, the radius is going to change as well. Recall that centripetal force divided by mass gives acceleration. So radius actually depends on the mass. And actually, if we look at the last formula, which relates angular velocity, oh no, from that we couldn't figure it out, that the radius is going to change. All right, so that's enough about the simulation. And let's evaluate another description of interaction, how magnetic field affects this quantity. Because force, which describes interaction, was related to acceleration, which describes motion. Well, we could alternatively describe interaction using concept of work. And work was related to what? A description of motion. And let me give you a hint. The law which described the link between interaction and motion was referred to as work energy theorem. So network was related to Eric, louder? Kinetic energy, correct. Change in kinetic energy was equal to work. Let's evaluate work performed on a particle due to magnetic interaction. Well, in order to determine work, I will have to consider a certain differential displacement and calculate scalar product of the force and the displacement. Right? This is by definition of work. Scalar product of force by displacement gives me the work. Now, this is a vector. What is the direction of scalar product? I'm giving you a tricky question. Scalar product doesn't have a direction. The result is going to be a number, right? Work is a number. All right. Now, let's write down explicitly the expression for the magnetic. Oh, well, actually, I wrote over here that that differential displacement is equal to product of velocity and time. Right? Where did I get it from? How is it that I could substitute ds with velocity multiplied by dt from the definition of velocity? This displacement divided by this dt will give me velocity, right? So if I multiply both sides of the definition by dt, I will get this expression. And now I am going to write down explicitly expression. Oh, no, I'm not going even to do that. I conclude that it's 0. Why? Well, how do we calculate scalar product of two vectors? Well, we can, if we know scalar components, we multiply appropriate scalar components and add the products, right? Now, how about if we know the angle and magnitudes? So it is going to be magnitude of the first vector times magnitude of the second vector times cosine of the angle between them. Now, what's the angle between magnetic force and velocity? 90 degrees. I mean, on the drawing it is 90 degrees, but I made the drawing, but is it always 90 degrees? Yes. Right? Because of this formula over here. Magnetic force is always perpendicular to velocity, which means that the scalar product is 0. So magnetic work performed on a particle due to magnetic interaction is always 0. Well, so what is the conclusion? That the magnetic, a magnetic field cannot change the speed of a particle. It can change its direction, so it can change velocity of the particle, but it cannot change the speed of the particle. The particle is going to move always with the same speed. I think this will be enough for today.